a classical communication problem using quantum entanglement. Okay, so let's first see a bit of what quantum entanglement is and what it can do. So for the purpose of this talk, you might think of a quantum state as a d-dimensional complex vector. And if the quantum state is shared between two parties, say Alice and Bob, well, it can exhibit entanglement. That is a quantum correlation that has no classical counterpart. But we're very interested in entanglement as a resource. And entanglement can be a resource for many nice things. And the thing we're going to use here is quantum teleportation. Okay? So we're going to see how teleportation works, and more importantly, what resources do we need to complete it. So suppose Alice and Bob has these nice teleporter machines that use entanglement in a way we don't know. But and Alice wants to teleport a d-dimensional quantum state. Okay, and we'll send it to Bob. So she puts the d-dimensional state into her machine, and poof, the state pops out on the other side. But look, it's upside down. It's rotated. Actually, the teleportation scheme can introduce d squared possible rotation when d is the dimension of the state, and Alice will know which one happened. So to complete the protocol, Alice can send just a classical message to Bob telling him which rotation happened, and then Bob will be able to correct the state back and add it. Okay? So it's important to say that we transferred some quantum information from one side to the other without any quantum channels, but just a classical message. So let's now see what is the communication problem that we address. And I would like to get help from an internet joke that I found on XKCD blog. So this is the color palette, okay? And these are the color names if you're a girl. And these are the color names if you're a guy, probably. Or maybe these ones, or maybe these ones. Well, it doesn't really know how to label this stuff, okay? So the question is, how many colors can Alice select without risk of confusion on both sides? Okay? So let's simplify a bit the situation here. And let's imagine that this is the color palette, and these are the only color names that Bob knows. So suppose now we ask Bob to label what maroon is. Okay? I would say, maybe it's purple, or maybe it's red. I don't really know. It's a bit confused. And tangerine can be either red or yellow for Bob. He doesn't really know. Asparagus can be either yellow or green. Teal can be either green or blue. And orchid can be either blue or maybe purple. It's not really clear. So with this joke between Alice and Bob, we just define the noisy communication channel. Okay, where this is the input-output graph. And so these are the inputs of the channel, and these are the outputs of the channel on both sides. Okay, and some inputs can be confused. In fact, we can draw another object out of the channel, which is the confusability graph of the channel, and this will be the crucial object. So in the confusability graph, the vertices are just the inputs of the channel, and two vertices are adjacent. For example, tangerine and maroon are adjacent because both can be seen as red by Bob, so the output sets intersect. But for example, tangerine and this other one, teal, cannot be confused, so they don't have an edge, because the first one has this output set, red or yellow, and the second one is either green or blue for Bob, so Bob does not compute this. So we can forget the input-output channel, the input-output graph, and just concentrate on the confusability graph and ask our question. How many colors can Alice select without risk of confusion on Bob's side? So okay, she can select one, and Bob will interpret this as either red or yellow. She can select the second one, but Bob sees as either green or blue, so there's no confusion. But notice she cannot select any other, because this can be seen as blue, This can be seen as red by Bob, and this can be seen as green or yellow. So all other inputs will cause confusion. So for this particular channel, with this graph, so the answer is 2, but in general, the answer is the independence number of the confusability graph. That is the largest subset of vertices, such that no two are adjacent. Okay, so let's see how we can use this independent set that we found in order to communicate over a noisy channel. Okay, so we have this graph. This is the independent set, and we labeled the two elements like message 1 and message 2. And suppose Alice wants to send message 2 to confuse Bob. So she will input this color to the channel, and Bob will either see red or yellow, and suppose he sees red, he knows that red could not be caused by message 2, because if this is either green or blue. So he will be sure that Alice wanted to send message 1. Okay? And in general, for many users of the channel, we count the average number of messages per use that can be sent by Alice without confusion, and this is called the zero-error channel capacity. Okay, so now let's get to the hit in the talk, and let's see how we can use entanglement or teleportation to improve the solution of this communication problem. So we have this confusability graph. We know that the independence number, alpha, is an important parameter for the classical solution. But for the quantum solution, we need another parameter, which is d, the minimum dimension of an orthogonal representation of the graph. So an orthogonal representation is an assignment of vectors, one vector per each vertex, such that adjacent vertices get orthogonal vectors. Okay? So now consider what we said before. Quantum states are vectors. Okay? They are d-dimensional complex vectors. And quantum mechanics tells us that two quantum states are perfectly distinguishable if and only if they are orthogonal. And to teleport a d-dimensional state, we have seen before, it is sufficient to send one out of d squared classical messages. So this suggests the following. So we can have the same setting as before, but now we label 5 messages, one per vertex. And we also give the players a teleportation machine. So Alice wants to send message 1. As before, she sends through the channel the corresponding input. But now Bob sees either red or yellow, suppose he sees red. He doesn't really know if red was originated by message 1 or message 2. Both of them can be seen as red by Bob. So luckily, Alice can send the vector from the orthogonal representation of this vertex through the teleportation. Bob will get a rotated version of this vector, and Alice will know which rotation out of d squared happened. And now, if d is sufficiently small and the independent set is sufficiently large, she can use the channel again and send the additional message to Bob through an independent set. And Bob will have the correct state now, and since he has to distinguish which one of these two states he has, and those are orthogonal, he can make a measurement and check, oh, it was the first one, it message 1. So with the use of entanglement, we increase the number of messages that we could send. And okay, this was a toy example, but in general, if a graph has sufficiently small orthogonal representations and a large independent set, then we can use teleportation to boost like the Shannon capacity. And we found a family of graphs that give us unbounded improvement in the sense that you can tell me, oh, give me a graph that has this improvement, and I can find one, okay, from this family. And on the way, we found many links with classical graph theory. For example, we defined a quantum independence number in this setting. Thank you very much.
number of classical users of the
Yeah, that the average number is still larger than Schwarzschild. For example, what you can do, the average number of matrices